In this video, we're going to take a look at linear transformations of roots. Now, to conclude this chapter here on roots of polynomials, we will now consider linear transformations of roots. So, for example here, if the roots of a cubic equation are given as alpha, beta, and gamma, then we need to be able to find the equation of a polynomial with the following roots here. So, for example, alpha plus 1, beta plus 1, and gamma plus 1, or 2 alpha, 2 beta, and 2 gamma. So a linear transformation then will be of this form here. So W is equal to Px plus Q here. Okay. And we use W here as the variable for our new polynomial just to avoid confusion. So the important question here then is, how do we find our new polynomial? Well, we just start then by rearranging W equals Px plus Q here to give X equals W minus Q over P. So nice and straightforward, really. All we're doing is rearranging and making X subject. We then substitute this into our original polynomial. And finally, we expand and simplify where necessary. Now, just note here that exam questions will often ask for integer coefficients for your equations. So what I would recommend here as almost like a best practice when doing these kind of exam style questions for linear transformations of roots is that you always give your equation with integer coefficients just to avoid any potential errors there, as noted here with this final line. Okay, so a very quick introduction there, but that's all we really need then for linear transformations of roots. So let's take a look then at one example here for linear transformations of roots. So let's get started then with this example here. So what do we have for this question? Well, as we can see then, we're given this cubic equation here, and we're told that it has the roots alpha, beta, and gamma. The question then says, without solving the equation, find equations with integer coefficients that have the following roots here. So let's begin then with part A here. So for part A then, this is for the roots of 2 alpha, 2 beta, and 2 gamma then. So what do we do to begin with here? Well, the first thing that I'm going to do here then is let W, so we let W here be equal then to 2x here. Now don't forget that W just represents our linear transformation here. So next what I'm going to do here then is rearrange this equation and make x a subject here. So in that case then, nice and straightforward here, we find that x is equal to W over 2. Okay. And now what I want to do here then is substitute this back into the original equation here. So if we do that then, what we get here is W over 2 all cubed. So W over 2 all cubed here. Then get minus here, W over 2 all squared. We then have two lots here of W over 2. And then finally here, minus 4. And that is all equal to 0, right? So that's equal to 0 here. So now let's expand and simplify here then. So expanding to begin with, we get W cubed over 8. So W cubed over 8. We then get minus W squared over 4. So W squared over 4. The 2's here will just cancel, right? So they cancel and we get left with W. We then have the minus 4 here. And that is all equal to 0. Now, we're not done here because don't forget, we do need integer coefficients. So to obtain integer coefficients here, all we're going to do is times through by 8. So if we do that then, what we get here is W cubed. You then get minus 2W squared. We have 8W then. And then finally, minus 4 times 8, we get minus 32 there. Okay. And that is all equal to 0. Okay. So there we have it. That is the solution to part A. Now for part B then, as we can see here, the roots are alpha plus 2, beta plus 2, and gamma plus 2. Now, we might need a little bit more room here, so let me just quickly clear the screen, and let's have a go then at part B. So we've cleared the screen then, let's have a go now at part B. And as we've already mentioned, we have the roots here of alpha plus 2, beta plus 2, and gamma plus 2. So for part B then, again, we just start here by letting W, so let W here be equal then, well in this case, given that we've got alpha plus 2, beta plus 2, and gamma plus 2, W is equal to x plus 2 here. Okay, and again we just rearrange here and make x a subject, so nice and straightforward here. x in that case is equal here to w minus 2. And all I want to do now then is substitute this here back into the original equation. So if we do that here, what we get then is w minus 2 cubed. You then get minus here, w minus 2 squared. We then have two lots here of w minus 2. So two lots of w minus 2. And then finally here, minus 4. And that is all equal to 0. Now, in terms of expanding, say, w minus 2 here, so this is w minus 2 to the power of 3. Expanding this, you can use the binomial expansion if you want to. Given that we've got this w minus 2 to the power 2 anyway here, I'll just do it by hand. But like I said, binomial expansion is absolutely fine here. So w minus 2 squared, so let me just write this down here. So w minus 2 squared here, so that would give me w squared. I'd get w times minus 2, so that's minus 2w, but we'd do that again, so I get minus 4w in total. And I've got minus 2 squared, so that gives me positive 4 there. Okay, and now I'm going to times this here by itself again, so w minus 2. So w minus 2 times by this quadratic here then, w squared minus 4w plus 4. So if we now expand this out here by hand, what we get then, well, I get w times w squared, so that's w cubed. I get w times minus 4w, so that's minus 4w squared. Oops, that's supposed to be a squared there. And I've got w times positive 4 here, so I get plus 4w. So that's the first term complete here. Just do the same now with the minus 2 term here. So minus 2 times w squared. I get minus 2w squared here. I then got minus 2 times minus 4w. So just be careful with the signs here. We get plus 8w. So plus 8w here. And then finally, minus 2 times 4. I get minus 8 there. Okay. So that's the first part here then. So let's just write this down. So we get w cubed minus 4w squared plus 4w minus 2w squared. We then have 8w. And then finally here, minus 8. Okay, so that's this first part here complete. This part we've already expanded. We did that here. I then get minus here. I'll put all of this in a bracket just to make it clear. So I get w squared minus 4w plus 4. We then have two lots here of w minus 2. So that's going to be 2w and minus 4. So 2w and minus 4. And don't forget the minus 4 here at the very end. And this is all equal to 0 then. Okay. And then at this point here, it's just a matter of simplifying. So collecting like terms where we can. So what have we got here then? So I've got 1w cubed here. I can't do anything with that. So we get w cubed. Okay. I've got minus 4w squared here. I've also got minus 2w squared. So that's minus 6w squared. And we've got one more minus w squared here. Okay, so in total then we get minus 7w squared. Okay. Then for the linear term here, well, I've got 4w, 8w, so that's 12w. We've then got minus 4w, so just be careful here. So that's the same as plus 4w. We've also got a 2w here, so I've got 6w, 8w there, so that's 14, plus another 4, so that's 18w in total. So plus 18w. And then finally here, so what have we got? Well, I've got minus 8. I've then got minus positive 4, so that's minus 4. So minus 8 minus 4, that's minus 12. And then minus another 8 here, so that gives me minus 20 there. Okay. And this here then is all equal to 0. Okay. And there we have it. We already have integer coefficients, so that's fine. So there we have it. So that gives the solution there to this example, this question. And that actually brings the end then of this video here on linear transformations of roots.